So, good evening. I welcome to this live interaction session. So, let me just share my screen. Is it visible? Okay.
Not yet, sir.
Okay. So, if you have any doubt in any of the lectures or you want me to discuss that, then you can tell. Otherwise, we can discuss it later after the solution of assignment 3.
No doubts.
Okay. So, let me then share questions from assignment 3 and then some issue. Here is question number 1. It says we need to determine the cases in which the group H is isomorphic to the group G. So I hope you guys know what is group isomorphism.
Yes, sir.
Okay. So what about the first option? So we are given G to be the GL1R, the group of invertible 1 cross 1 matrices over R, and R star is the multiplicative group of non-zero real numbers. So are they isomorphic?
Yes, sir.
Okay, what is isomorphism?
So, suppose A is some matrix belonging to G, that will be a form that will contain a single value,
Yes.
say A. So I map that matrix to uh, A in R star.
So G is your GL1R, H is the R star. So it's a 1 cross 1 matrix, so there will be just a single entry and you will map it to just A, right?
Yes.
And that's it. So phi is an isomorphism and hence these groups are isomorphic. It's a very easy question to start. Then let's move to the next question. Z with the additive group of integers and GH be two different infinite subgroups of Z, then are they isomorphic?
Yes, sir.
Okay, what is isomorphism or what is the reason behind it?
So G will be of form NZ, where N belongs to Z,
That
and
N equal to NZ and M equal to MZ, the two subgroups of Z, then
so for some element belonging to H, it will be a form, let's say NA.
right.
Then I map it to MA.
So this, right. So you are saying H, I should not use M, let me just write K here. So an element N is mapped to, sorry, element and A is mapped to MA. Why it is an isomorphism?
Mm, it's 1 to 1. So
So
if there are,
shall I check? Or you know how it is 1 1 and on to?
yes, sir. So suppose NA1 and NA2 are okay. So
Well, first of all, we should check that phi is an homomorphism, right?
yes, sir.
So phi is an homomorphism. For that, uh, we write like that. So let NA1 and NA2 be two elements in H. Then phi of NA1 plus NA2 is just phi of N of A1 plus A2. And by the definition, this is M of A1 plus A2, which is M of A1 plus M of A2, and that is phi of A1 and phi of A2. So this implies phi is an homomorphism. So is a homomorphism. Okay. What about 1 1? So let phi of A1 equal to phi of A2 for some A1, A2 inside H. This will implies, uh, oh, I should write phi of N A1. That would be good. This would implies M A1 equal to M A2, and that is M of A1 minus A2 is now there are two possibilities. Either M is 0 or A1 minus A2 is 0. Now since K is an infinite subgroup of Z, therefore M is non-zero. So that's the place where the infinite subgroup of Z is being used. If M is 0, then it's K is just singleton 0, right? So this will implies A1 minus A2 is 0, and hence A1 is A2. And which implies phi is injective or 1 1. Now onto part. So let some B belongs to K, then there exists A belongs to Z such that B is equal to MA, and uh, thus phi of NA is equal to MA is equal to B, which implies phi is onto. and hence it's a isomorphism. Okay. Okay then. So maybe we can move to the next part. So we have S3, the group of the symmetric group in three letters, and then the H is the group of complex sixth root of unity. So are they isomorphic?
No, sir.
Reason?
So here the complex sixth roots of unity is a cyclic group, but then S3 is not cyclic.
S3 not even abelian. Okay.
Yes, sir.
So since S3 is non S3 is a, and we have seen that under group homomorphism, the abelian part, abelian as well as the cyclic part remains uh, as it is. If it is 1, 1, then onto the image that part holds. And that means if the homomorphism is an isomorphism, then if the domain is an abelian group, if and only if the codomain is abelian, and same is the case with the cyclicity property. So since S3 is a non-abelian group, it's a non-abelian group, and uh, the group of complex sixth root of unity is cyclic. Therefore, G is not isomorphic to H. So this is your G, and this is your H, or it is already given in the uh, question. So let's not make it more clumsy. Okay. So what about the next one? As GL2R and Z,
Not isomorphic.
not
One
isom.
countable, the other is uncountable.
What's the argument? Why I have waited page to the at the wrong place. Yes. Brenda, you were saying something. What's the reason?
Um, so G is uncountable, but H is countable. So there can't be any bijection.
So we haven't. So there can't be any bijection. That's also true. Uh, what if we want to say something more group theoretic? That is also correct. So GL2R is uncountable because R is uncountable, and H is countable. That is okay. But can we get an answer concerning some group theoretic property? So whatever you said is right. There is no bijection, so there is no isomorphism, right? So let me first write your argument. So GL2R is uncountable and Z is countable. Therefore, there exists no bijection between Gl2R and Gen. This implies Gl2R is not isomorphic to Z. Is there any other answer to this question without concerning the bijectiveness, means, or without this countable uncountable argument? So let me tell you one more answer. So Z has no non-trivial element of finite order, right? Except one, every other element has infinite order. Sorry, except zero. Yeah. Do you agree with this statement?
Yes, sir.
Order, you know that a raised the smallest uh, in positive integer such that a raised to n is identity.
Yes, sir.
And what about GL2R? But GL2R has non-trivial elements of finite order. Can you just give me one such example? For a, what about this matrix?
The order is
This has order 2, right? Right. And can we get more matrices of finite order? Oh, do you know rotation matrices?
yes, sir.
So rotation matrix of order n has, can you give me the rotation matrix for uh, n order?
Sorry, sir. I don't remember the.
I
Um,
don't remember, I need to check. So, do you know reflection matrices?
yes,
All,
sir.
all reflection matrices will have order 2, and all rotation matrices will have order n. So there are actually infinitely many elements of uh, finite order. Let me just see the rotation matrix. I think it is cos theta sine theta minus sine theta cos theta. So uh, this is rotation or reflection. I'm a bit confused. So if you multiply this matrix again with this will be cos square theta minus sine square theta. That is cos 2 theta. And then uh, this part will be right sine 2 theta. Here we will get. Okay. So Dial is saying something. Yes, tell. Good evening. This is, I think, rotation matrix of so if we consider R n 2 pi by n, that is cos 2 pi by n and sine 2 pi by n, then this matrix will have order n. So you agree? Let me just write reflection matrix also. Reflection matrices will have order 2, irrespective of uh, the theta chosen. I think it is how to write maybe small r theta. It is cos theta sine theta minus sine theta and uh, oh, that is same. So maybe sine will come some other direction. Let me just recheck it. Will this work? No. Now I missed that notes. But you got the point, right? All reflection matrices will have order 2, while the rotation matrices will have order n. They are not able to find. So in terms of it in fact forms a group. Uh, Here it is. So first of all, this minus sign will change. Although if you take minus here also, then there won't be much issue because it just uh, differ by some axis, I guess. But with convention we take here. So I will also take here. And now reflection matrices are, you take cos 2 theta, sin 2 theta, and sin 2 theta and minus cos 2 theta. So cos 2 theta, sin 2 theta, minus sin 2 theta, and cos 2 theta. This is for reflection by an angle theta. Oh, I make a mistake. Minus should come here. Now you can check that its square is, it should be identity. So notation matrix is a reflection matrix. So there is one more approach to start your group theory course, and that is through symmetries. And if you are following that approach, then these matrices are defined in very beginning, and then the course develops as a symmetry course. Means then as symmetries of certain objects, the group is introduced, and all the concepts like order and other things are explained in terms of symmetries, and that also gives you motivation that why group theory is important. So you should keep these concepts also in mind, so that if you are at some point of time you want to read that through that approach, then it should be feasible for you.
Okay, sir.
So clearly this has order 2. If you take the square, then this will be cos square 2 theta plus sin square cos 2 theta, that is 1. And this part will vanish. Here will be 0, here it is 0, and here you will get 1. So this has order 2, and all these rotation and reflection matrices are depending on the parameter theta. So there are infinitely many of them, and in fact there are uncountably many, because theta here belongs to R. There are uncountably many elements of finite order, but Z has no non-trivial element of finite order. So the first argument that you gave was the groups are countable and uncountable, but in fact, if you just look at the elements of finite order, then that kind of cardinality difference is even more. Here, there is zero element of finite order, non-trivial, and here there are uncountably many elements of finite order. So they not just differ as sets, as groups, they differ a lot. Okay, so that was the point I want to emphasize. Okay, but the answer that you gave is also absolutely fine. Okay, so if it is fine, then let's go to the next question. For a group G, let Ng denote the least integer such that X and G equal to identity for every element X belongs to G. Then we need to choose the correct statements. So does anyone knows the name of this least integer? What it is called in group theory? The least integer such that X raised to that integer is identity for every element X in G. So this is called the exponent of the group G. So exponent of the group G. And this is always less than equal to order of G, provided, of course, your G is finite. In infinite, this may not make sense. Although for infinite also you can talk about such a element, and then this is trivially true. It's because order of G is infinite, but generally we talk about exponents in finite for finite groups. So yeah. So what about the first option? G is a finite group of order n, and then Ng is less than equal to n. So this is just what I said. This has to be true. Uh, okay. So you know why it is? We have already seen that x raised to order of G is identity, right? And it is the least integer which is satisfying this property. So that should be the case. That is one way to see, but that argument fails when your G is infinite, because then x raised to order of G will become x raised to infinity, right? So you may need to split it in two cases. First is when G is a finite group. Then for finite group, x raised to order of G is identity. And since this Ng is the uh, least smallest or least integer such that this holds. So this has to be less than equal to order of G. Second case is when the group is infinite. So when the group is infinite, this part is infinite, and this is the least integer such that x raised to Ng is identity. So if that integer exists, that has to be finite, and thus exponent of the group is less than equal to order of G. So in both the cases, it holds if it exists. If it doesn't exist, then we won't say anything. And that will happen only if the group is infinite. Because for finite group, this will always exist and it will always be less than order of G. Clear?
Yes, sir.
Okay. So if G is a finite group of order n, then can Ng is equal to n? For n?
Not true.
Not necessarily. What is the example?
Line group.
Klein group. Very good. Klein counter example is Klein square. What about the third one? Others can also speak. Don't worry if you're wrong, then that is fine. So if G is a group of order 6, then Ng is equal to 6.
This is true.
So the B option is not true in general. For any n, this may not be true, but for n equal to 6, you are saying that this may be true. Why?
So I think it's Cauchy's theorem, right? So using Cauchy's theorem, the elements of order 2 and there exist also elements of order 3. So once I know that there is some element of order 2 and some element of order 3, then so in order to get the least element such that um, a power n is
Yes, yes, we are on the right track.
has to be G6.
There was a disturbance in your voice. Can you just repeat your argument once?
Sir, am I audible clearly?
Now you are audible.
Yes. So through Cauchy's theorem, that there is some element of order 2 and also some element of order 3. So um, since there are elements of order 2 and element order 3, so if a power n has to be identity for all elements, it has to be LCM of 2 and 3, which is
Right.
6.
And thus
Um,
the least integer should be greater than equal to 6, but we already know that it is less than equal to n, which is 6. So it is precisely 6. Good. So by Cauchy's theorem, Cauchy's theorem says that if P divides the order of G, then there will be an element of order P in it. So that's what I mentioned in, I think, very first or second class, that when we were doing it for squares, that there is just a theorem for every prime number, and that is the Cauchy's theorem. By Cauchy's theorem, there exist elements of order 2 and 3, and which implies Ng has to be greater than equal to LCM of 2, 3, which is 6, and by part A, Ng is anyway less than equal to order of G, that is 6. Thus, Ng has to be 6. And in this particular example, you can also verify it by taking the groups. So, how many non-isomorphic groups of order 6 are there?
Sir, can you repeat your question?
There are, hello, you're not audible, Prerna.
Sir, can you repeat your question?
So I am saying how many non-isomorphic groups of order 6 are there? Means how many different groups of order 6 are there?
Well, that's the cyclic group. There's S3. So,
There is a cyclic group Z 6, right? And S3.
uh, yes, sir.
Do you know any other group of order 6?
Um, no, sir.
What about dihedral group D3 or D6? Dihedral group of 6 elements? Have you heard about the dihedral groups?
Yes, sir.
So what about dihedral group of order 6?
Not, isn't it similar to S3? I'm not sure.
It is isomorphic to S3. So there are just two choices for groups of order 6. One is the for the abelian case, that turns out to be cyclic as well. So that is Z6, and the other is the non-abelian case, and which is S3, and that is also isomorphic to D3 or D6, whatever notation you write. So there are just two groups, and for both the groups, you know that Ng is 6, right? For S3, it is 6, and for cyclic group of order 6, it is definitely 6. Okay. But the first step, that there are just two groups of order 6, that requires a bit of work. So uh, that's why this approach is better. Okay. But you should know that also, that whenever there is a question concerning groups of fixed order, if you know all groups of available for that order, then you can directly answer the question without even knowing some important theorems like Cauchy's theorem. And these kind of groups, uh, I think till order uh, 11, you can easily remember that what are the groups. Order 2 and order 3 are cyclic. So there is just one possibility. They are prime. For order 4, there are three possibilities. Either it is cyclic of order 4 or Z2 cross Z2. That is Klein group. So there is just two possibilities. There is no other possibility. There is no non-abelian group. For order 5, it is cyclic. Just one possibility. First non-abelian case comes for order 6. There are just two possibilities. Then for order 7, it is again prime. So uh, it has to be cyclic. For order 8, there will be two cases, abelian and non-abelian. I leave it to you uh, to check how many non-abelian and abelian groups are there. There will be more than one non-abelian groups of order 8. So that is the first order for which you get more than one non-abelian groups. For 9, it is the only groups are abelian because there is, you will see there is a statement which says every group of order p square is abelian. So 9 is of the form p square, so it is abelian. And for order 10, so order 10 is of the form 2 into 5, right? Later, you
Yes.
will again see a statement saying that if the group is of order p times q, where p is less than q, then a very well-known structure for such groups is known, and through that you can see what are these groups. Then again, 11 is prime, so it is cyclic. So for small orders, there is a complete classification, and in fact, now people have done for several hundreds, but for practical purposes, it's good to know at least for the starting cases so that you have enough examples to work with. Okay. Okay, so that's just the motivation part. Now let's come back to our question. What about the D part? If Ng is 2, then G has order 2.
No. Again, the Klein group is an example.
Lane group is an example. For example is again the Klein group. Okay. So if it is clear, then let's move to the next part. We have to choose all the correct statements. If G is a group of order 23, then every subgroup of G is normal. Is it true?
Yes, sir.
Why?
So the only possible subgroups are the trivial group and the group G itself, and they are all always normal in the group itself. So
Why they are the only groups?
so 23 is a prime number.
Good.
So
Since 23 is a prime number, therefore, by which theorem you are saying this?
Lagrange theorem.
Lagrange theorem. Therefore, by Lagrange theorem, the only subgroups of G are identity and G itself. If you want, I can write it like that. And they are always normal. What about the second one? G is any group and X and Y are two elements of G, such that X has order 2 and Y has order 3, then the order of XY is 6.
Not true.
That is
Not true.
not true. Why? Any counterexample?
Yes, sir. So consider S3.
Good. So
So
G is equal to S3, X is equal to any order 2 element, that is 1, 2, and maybe Y you can take 1, 2, 3. Then what is XY?
2,
2, 3. Yes, order 2. What about C? G is a group of order 24, then every subgroup of G is normal.
not true.
Counter example.
Considering S4.
Okay, so first time we
they-
have going to S4. So
So if we
S4.
take
Mhm.
the identity and 1, 2,
So,
this is not a normal subgroup.
so G equal to S4 and take H to be the identity and 1, 2 group, that is the subgroup generated by 1, 2. Then H is not normal in, but this is not normal in G. Good. What about the last part? You have order 2 and order 3 element, but here the group is abelian. So for abelian group, does it hold?
Yes, sir. It's true.
Why?
So I have just considered the cases. Um,
You have considered.
so all the cases. So suppose I take X and Y. I consider XY square, XY cube, and so on. I
Mhm.
can show that this is true only for XY power 6. And for all others, we get uh, non-identity values.
Okay. So let G be an abelian group and XY belongs to G such that order of X is 2 and order of Y is 3. So we already know that XY raised to N should be Xn Yn, right?
Yes.
For all XY in G because it's abelian. Now, if 2 divides n. If 2 divides n, or let me write like that, if n is of the form 2k plus 1 for some k belongs to n, and 3 divides n, means n is divisible by 3 but it is not divisible by 2, then what will happen? Then xy 2k plus 1 will be x 2k plus 1 y 2k plus 1, and this, since this is divisible by, sorry, 3, so this will vanish, so this will be just identity, and this is because 3 divides n, right? And it has order 2, so you can write as x 2k time x, this is x, this is because order of x is 2, so clearly this is not identity, right? So
Yes.
all odd, so the order cannot be odd, right? Now, if
Yes.
n equal to 2k for some k belongs to n, and 3 is not dividing n, then again the same thing we can do, xy raised to 2k is x 2k y 2k, it has order 2, so this will vanish, we will just have y 2k, which is not equal to identity, since order of y does not divide n. So if y raised to something is identity, then order of y should divide that something. So here y is not dividing 2k, so y raised to 2k cannot, sorry, here order of y, that is 3, is not dividing 2k, so y raised to 2k cannot be equal to identity. So if it is divisible by 2 and not divisible by 3, then also it cannot be whole. Okay. Now this implies order of xy must be divisible by 2 and 3, and hence order of xy should be greater than equal to 6. But so one part is clear. Now for n equal to 6, xy raised to n is x raised to, oh, I should write just 6. x6, y6. In this, both the cases, x's is identity, y is also identity. So you have just identity time identity, that is identity. And this implies order of xy is equal to 6 because it is the least integer such that xy raised to n is identity. Okay. So is it clear?
Yes, sir.
Okay, so if you have any doubt in any of the question part, then ask. Otherwise, we will move to the next question.
No doubt, sir.
Okay, thank you. So what about others? They can also speak. Fourth question is again for S3. So you have S3 cyclic group of, and G to be the cyclic group of order 4, G prime to be the Klein 4 group, then A be the number of group homomorphism from G to S3, B be the number of group homomorphism from G prime to S3. We need to choose the correct answers. Yes. What are the number of group homomorphism from G to S3?
4.
4. Why?
Um, so, um, since G is cyclic,
Hmm.
I know that the identity maps to identity anyway, and if I know what the um, so the cyclic group is of form A square, and A cube. If I know what A maps to, then I know where the rest of the elements are mapping.
Hmm.
So, so A can either map to identity, or it can map to the 2 cycles or the 3 cycles. But if A maps to any of the 3 cycles, then A power 4 should again map to identity. But for any 3 cycle, um, if I take the 3 cycle power 4, I won't get identity. So A can't map to the 3 cycles,
Three
which
cycles.
leaves only the
It can
um,
either map to identity or any of the order 2 elements, right?
yes, sir.
So this is because let 5 be a homomorphism. If we know phi of 1 bar, then phi is completely determined. Now, since phi is an isomorphism, sorry, is a homomorphism, for any homomorphism, this always holds that phi of A should divides, oh, it's not phi of A, order of phi of A should divides order of A for all A belongs to Z. And in fact, this is true for any group that if you have a homomorphism from G to H, then order of A must be divisible by order of phi of A. So you know the proof for that?
Yes, sir.
Can you just recall?
Um, yes, sir. So,
Hmm.
so is the um, oh, sorry, I thought I'm just slightly confused.
So let's say A raised to N is identity. The order of A is N. So what will be phi of AN? Phi
Um,
of AN is phi A raised to N, right?
yes,
But
sir.
phi of an is also same as phi of identity because an is identity.
Yes,
And
sir.
phi of identity is identity. So let me just recall the proof. So let order of A is n, then
Sir, but here,
uh,
A, if A belongs to Z, then order of A would just be infinite, right? I'm confused about that.
here I am writing it. So it is Z fourth.
Oh, okay, sir.
But this holds for any group. For
Yeah,
any,
then I think I can prove this.
maybe I can write it as a statement for any group. Then we can show. So if phi from G to H is an is a homomorphism, and A belongs to G, be an element of finite order. Why I need finite order? Because I want this divide part to make sense. If order of A is infinite, then to say that order of IA divides infinite is uh, not uh, it's not good, right? So that's why to make sense, we need order of A to be finite. That's it. A be an element of finite order. Then uh, order of phi of A divides order of A. That is the statement, and the proof is if that order of A be n, then identity of H is same as phi of identity of G, and this is same as phi of A raised to n, and which is same as phi of A raised to n. And I have told you earlier that if some power, if some element raised to something is identity, then that something has to be divisible by uh, order of that element. So this implies, and I think I have also told you the uh, proof of it. So order of 5A divides order of so, n, which is order of A, right? Now this divides order of A, and why we were doing all these things? Because uh, order of we want to see the image of one bar, right? So order of, I think we spoke to the very last, order of phi of one bar should divides uh, order of one bar, right? And what is order of one bar in Z4, that is 4. So this implies pi of 1 bar can be uh, cannot, I should write, cannot be a 3 cycle. So it is either a 1 cycle or a 2 cycle. So pi 1 bar has 4 possibilities. That is identity 1, 2, 2, 3, and 1, 3. Okay. Okay. So first part is clear, I guess. So there will be
Yes.
4 homomorphisms from Z4 to S3. And what about the second part?
Um, there are 10, uh, 10 possible homomorphisms.
There are 10.
Yes, sir.
So can you tell me why?
Um, so, so I consider all possible types of homomorphism. So I know that the identity maps to identity.
So you
So
have calculated
now
all 10 by hand.
not all 10, but um, not all, I haven't manually calculated everything, but at least I think I can reason through.
Hmm.
Um, so so suppose there's some non-identity element in the client group.
The
So
voice is
again, here I know that for any sorry, sir.
Your voice is slightly breaking.
Um, is this better now?
Now it's audible.
Okay. So so again, here I know that um, any of the elements can only map to the identity element or the um, two cycles using the argument as before.
Right.
So so suppose I take some element from the client group, some non-identity element.
Hmm.
Now it has four possibilities. It can either map to one of the two cycles or it can map to the identity.
Right.
So suppose it maps to some two cycle,
Hmm.
and I take some other element from the client group, non-identity element.
Hmm.
Suppose it also maps to um some two cycle.
Hmm.
Then what happens is I have um, in so in the client group, if I take two non-identity elements, I get the other non-identity element, right?
Right. So basically, you
But
want to say uh, let
so
G prime be a
that would map to a three cycle, which is not possible.
okay.
So if some uh, non-identity element is mapping to some other non-identity element in the S3, um, so all the rest of the elements in the client group have to map to the identity itself.
Can't they map to the two cycle again? Same two cycle?
No. Even if that's the case, I would have so for this, well, I took a case by case basis. There's it in, I haven't thought about other proof,
Okay. So,
but taking case by case basis, I run into some contradictions and end up with only one element mapping to one element and rest of them mapping to zero.
so what are your 10 homomorphisms then?
So suppose I take 0, 1,
Hmm.
I map 0, 1 to 1, 2 and 1, 0 and 1, 1 to E. Or I map 1, 0 to 1, 2 and rest of them to E. Or I map 1, 1 to 1, 2 and rest of them to E. I could repeat the same for 1, 3 and 2, 3. So there's 9 possibilities here. Or I could map all of them to E. So there's total of 10 possible homomorphisms.
Okay. So let me just recollect whatever you said and uh, also fill out the gap that why can two elements map to the same two cycle, right? So first of all, from previous part, so yeah, right. Um, from previous part, we know that order of phi A and order of phi B and order of phi AB, they all belong to either one or two, right? Because they have order two. So they cannot map to uh, three cycles, right? Now, case one, if phi A and phi B maps to different two cycles, then what will happen? Then and say that phi A be some alpha beta and phi B be some alpha gamma, where beta is not equal to gamma and alpha beta gamma belongs to 1, 2, 3, right? So this will implies phi of AB, that is phi of A times phi of B is alpha beta alpha gamma, and that will be alpha going to gamma, gamma going to beta, and beta is going to alpha again. So it's a three cycle, which is a contradiction to order of phi AB is 1 or 2. Definitely they cannot map to different 2 cycles. Now case 2, if phi A, similarly you can say that let me this right. Similarly, uh, instead of maps to, I can should write cannot be, because this is already a map. Um, it is already an image, right? So second part is similarly, uh, phi B and phi AB, and other option is phi A or phi A and phi AB. They can also be, cannot be different 2 cycles. Same argument will work because AB times B is A, because B is of order 2, and A times AB is B, right? So you can get the other element using these two. So they cannot map to different 2 cycles. I have written it wrong. So this completes the first case. Case 2. If phi A and phi B maps to or cannot be phi or R equal and of order 2. That means they are mapping to same 2 cycle. So let phi A is equal to phi B, and that is equal to, say, alpha beta or some alpha beta belong to 1, 2, 3. And of course, they can, we are assuming that they cannot be same. Then what can be the issue? This implies phi of EB is phi of A phi of B, which is alpha beta times alpha beta, and that is identity, right? So you have this homomorphism. Phi is from G prime to S3 such that EB is mapping to uh, identity of G prime is mapping to identity of S3, and A is mapping to some alpha beta. B is also mapping to the same alpha beta, and AB is getting mapped to identity of S3. So do you see any problem in that? We need to check the homomorphism, right? So we need to just see this what happens to phi of these elements, because this is anyway doesn't play any role in that. Phi of A, phi of B is same as phi of AB. What about phi AB times phi B? That is also phi of A, and phi A times phi of AB, that is also phi of B. So this is a homomorphism. You see any problem in that? So check that phi is a homomorphism. And how many of them are, how many such homomorphisms are there? There are three such homomorphisms, because there are three possibilities for alpha beta belongs to S3. Okay. Uh, Now there can be another case, case 3, which says one of phi A or phi B is right exactly one of phi A, phi B has order 2. So let order of phi A is 2 and order of phi B is 1, and so let again phi A is some alpha beta, alpha beta belongs to 1, 2, 3, and they are not same. So will it be a homomorphism? It will be then phi from G prime to S3 such that A is mapped to uh, alpha beta, B is mapped to identity, and where AB will be mapped to? AB will be mapped to the product of uh, so this will be just phi A times phi B, which is alpha beta. So you can check that this will again be a homomorphism. Is a homomorphism. And how many choices are there? there are three such choices for phi. Similarly, if we assume the other thing that order of phi a is 1 and order of phi of b is 2, then uh, similarly, if we assume this, let me just rewrite this. Similarly, if this is the case, then there are three choices for phi, choices for homomorphism. So till now we have 3 plus 3 and 3, 9 choices. And the last case is order of phi A is equal to order of phi B, and that is 1, which implies phi of A is same as phi of B, and that is identity of S3. And this will implies that phi of AB is also identity of S3, and hence phi is the trivial homomorphism. Now, Prerna, are you getting more homomorphism? So you also said 10. I am also telling that there are, so we have already got 10, but three of these homomorphisms were not there in your list. So do you know why?
Um, well, no, I was wrong. I somehow did some mistake and still got 10 of them. But I see now why I was wrong, but I agree with your answers.
So what was wrong in your counting?
Oh, so I thought if I mapped some non-identity element to some non-identity element, I could map rest of them to the identity. But here, I've seen the case. So if one non-identity element has mapped to some two cycle, then there's some other non-identity element which has also mapped to some two cycle and not the identity. So this finally, considering all this, they
So
finally add up to
three
10.
of your options in which you have mapped, say, A to some order two element and the others to identity, that will not be a homomorphism, right?
Yes, sir.
So you were saying, so your all the non-trivial homomorphisms are of that kind only, right?
Yes, sir.
So none of them will be homomorphism. Okay. So
Okay,
here
sir.
the idea is the group is generated by two elements, A and B. So if you know the image of these two elements, the image of the third element is fixed based on the image of A and B. And that's a very common trick to find homomorphisms. You map the generators to certain elements, keeping all the factors in mind, and that will fix the image of all other elements. So you have no choice for the other elements. You are fixed if you are fixing the image of some other element without considering the image of the generating elements, then you might not end up with a homomorphism. Okay.
Okay, sir. Got it.
So since uh, G prime is generated by AB, therefore the above list of homomorphism, above list of homomorphisms exercise is complete. And hence, there are exactly 10 homomorphisms from G prime to S3. Okay. Yeah. So, okay, that is fine. We can move to the next part. Okay. So, we need to find all the options in which H is not a normal subgroup of G. So, first is the additive group of complex numbers and the additive group of integers. Is H a normal subgroup of C?
Yes, sir. It's abelian.
It's abelian. So since G is abelian and H is already a subgroup of G, therefore H is normal in G. Okay. What about the second one? You have 2 cross 2 invertible matrices over reals as G and subgroup of diagonal matrices as H. So is H normal in G?
Not normal.
Or so you need to tell me some element which is not closed under the conjugation.
Okay, so consider 1002.
1002.
This belongs to H.
Mhm.
And take 1101.
This is inside G.
And inverse of the element in G is 1 minus 101.
Just write A to be this and G to be this so that we need not to write the matrices again and again. Then B inverse is 1 minus 101, right?
Yes, sir.
And what is uh, B A B inverse? This is 101 and 1002, and this is 1 minus 101. So I need to calculate this. So first uh, column will come as it is 10, and last row will come as it is. Only this entry will change, right?
Yes, sir.
Please check the calculation if I'm wrong. Here also, since this is identity column, so first column will come as it is, and the first column will come as it is. Last row will be multiplied by 2, and what is this? -1, and this 1, right?
Yes, sir.
I hope my calculations is correct. So this is not inside.
Correct.
Ouch. Good. So H is not normal in G. What about the third one? G is the group of invertible n cross n matrices over real, and H is the subgroup of invertible n cross n matrices of determinant 1.
Here H is normal.
Reason?
So for any invertible matrix, determinant of A times determinant of A inverse will be 1.
But here A and A inverse are
And
from your G.
yes, but determinant of A times determinant of A inverse is always 1. And determinant of n belonging to H will also be 1. So determinant of A in A inverse will also be 1.
Okay. And determinant of A, so B inverse is determinant of B, determinant of A, and determinant and 1 upon determinant of B. So determinant of B inverse is always 1 upon determinant of B. So this will cancel out, and this is 1. So this will be 1. This implies B inverse belongs to H, and hence H is normal in G. So let's move to the last part. G is S5, and H is the subgroup of permutations which fix 5. Is it normal?
Not normal.
Then give me some element for which this doesn't hold.
Okay, so considering E and 2 cycle 1 3,
Consider
this is a subgroup. The
uh,
identity and 1 3.
so can you just repeat once again?
Oh, so the subgroup I am taking is consists of identity and the 2 cycle 1 3.
Oh, subgroup is already given. You need to check whether H is a normal subgroup of G.
Oh, I'm sorry, I misread the question.
So H is a subgroup of permutations which fixes 5. So what if I take uh, this thing? So 1, 2 belongs to H, right? It is fixing 5. And the element, say 1, 2, 5 will be there inside G. Then what can you say about uh, 1, 2, 3 inverse? 1, 2. I should write B inverse notation, no? So this will be, here it should be 5. 1 2 5, 1 2 1 5 2, right? What it will be? So 1 is going to 5, 5 is going to 1. So 1 is fixed, right? 2 is going to 1, 1 is going to 2, then 2 is going to 5. 2 will come to 5. 5 is going to 2, 2 is going to 1, and then 1 is going to 2. So 5 will go to 2. So this will stop here. And other elements are not there here in this. So they will be fixed. 3 and 4, element 3 and 4 are fixed. So this will not be inside H because it is not fixing 5. It is mapping 5 to 2. Okay. So in fact, if you consider S3 and with the same kind of definition of H, say you have instead of S5, you have the permutation group 1, 2, 3, uh, S3, right? And H is any subgroup of permutation which fixes a particular number, then that subgroup will not be normal due to the same reasoning. This implies H is not normal in G. Let's move to the last part of uh, the assignment. We have close to 15 minutes. So if we have some time left, then we will see some extra problem. Or if you have any specific question to discuss, then we can discuss. Okay. A group of order 128 cannot have an element of order 4.
Not true.
Not true.
So
Why?
consider Z128.
Consider Z 148. What will be the
Um,
element of order 4?
so if A is the generator, then A power 32. So the
So what? A
group
power
generate
32.
A power 32 will have order 4.
So simply 32. Uh, yes, you are also right. I am taking 1 to be the generator, but this holds for any generator, right? So if 1 is the generator, 1 raised to 32 is just 32, right? What about the next part? The group of order 128 cannot have an element of order 3.
This is true.
This is true. Why?
3 is not a divisor of 128.
Good. So since 3 is not a divisor of 128, therefore Z 128, not Z 128. Therefore, a group of order 128. And so if you, so, so this is due to what theorem?
Lagrange.
Lagrange's theorem. So if there exists an element of inside the group, then the subgroup generated by it uh, will be there inside the group, and the order of that subgroup must divide the order of the G, and the order of that subgroup is precisely the order of the element, and thus the order of that element must divide the order of G. And here 3 is not dividing 128, so there cannot be an element of order 128. So group of order 128 cannot have an element of order 3. What about the next part? C. A cyclic group of order 468 has exactly one subgroup of order 52.
This is true.
This is,
This was done in the practice problems.
oh, this was also done in practice problem. So for any cyclic group, there exists a unique subgroup corresponding to the each divisor of the order of the G, and those are precisely the uh, subgroups of the cyclic groups. So here, uh, 52 is dividing 468, right? How many times? 9 times, right? So
Yes, sir.
since 52 divides 468, or I should write completely, otherwise this looks like fraction. Divides 468, uh, therefore, uh, there exists a unique subgroup of order P2 in Z468. And these not true for the same reason, because 32 is not dividing this, right?
Yes, sir. It's not dividing.
32, it doesn't divide, right? Or it's
Yes, sir. It doesn't divide 468.
468. Therefore, there exists no subgroup of order 32 in Z468. So, if you have some question to discuss, then you ask. Otherwise, I will discuss some problem.
No specific questions, sir.
Okay. So let me give you some problem from the previous year assignment. This is extra question. Uh, We can ignore this marks because it's already written. So yeah. Determine the following cases. In which of the following cases H is isomorphic to the group G? First case is when both are of order 8.
These need not be necessarily isomorphic. One could be abelian, one could be non-abelian.
So what is, you need to tell me then one non-abelian group of order 8. You know any?
I need to think.
You know the quaternion group or the dihedral group? In fact, if you take both the non-abelian, then also it's not true. And if you put the condition that both are abelian, then also it's not true. So there are more than two uh, possibilities for abelian groups, and there are precisely two possibilities for non-abelian groups. So let me just do the job easier for this for you. So take Z8, uh, take Z equal to Z8 and H equal to Q8. You know what is Q8?
Sir, is this like extension of the Klein group? So
Mm, yes, somehow you can say that. H, right?
yes, sir.
So somehow you can say that, but or maybe not, because this group will have only so it actually depends that how you are looking at it. So one way of saying something is the extension is that the first group is sitting inside the second group. So that is not the case here. Client group is not a subgroup of this group. Second is uh, client group is generated by two elements, and both of them are of order 2, and this group is also generated by two elements, and both of them are of order 4 instead of 2. So as you can, if you consider the generating thing, then they look similar. Uh, but so it depends. As I said, it depends that how what you mean by something is an extension of something else. Okay.
I meant the second one, sir.
Okay. So where Q8 is this 1 minus 1 I j and uh, uh, shall I just write k, or I will just write ij, I, or maybe k, and then minus I minus j minus k, and such that you have so many properties. This is identity, this is minus identity, so I'm minus I square is I4 J4 K4, that is uh, identity, and you have ij to be k, and then you have ik to be, or ki to be j, and jk to be I. I think similarly you can find that what is I. So maybe I'm writing more than required. The group may be determined by fewer relations, but that's just for your information. So Ji is minus k, and kj is minus I. And of course, I is an identity element. So this is a non-abelian. You can clearly see that ij is k and ji is minus k. And k is not equal to minus k. Then these are different elements. Since Z8 is abelian, even it is cyclic, and Q8 is non-abelian. Therefore, G is not isomorphic to H. What about the second part?
Sir,
Huh?
so if I consider this group of uh, tuples,
Huh.
so if there are um, three places, I could have either mod 1 or mod 0, same like the Klein group, but then there are three uh, three places. Then this would be isomorphic to Q8, right?
I couldn't understand.
Um,
What?
so it's same like the Klein group, but then there are instead of two coordinates, there are three coordinates. So if I consider that group, it would be isomorphic to
You
um,
are saying Klein
Q.
group is generated by two. You are taking it to be generated by three elements.
Um, so Klein group consists of 0, 0, 1, 1, 1, 0, and 0, 1, right? So in this new group, they say the group would consist of 0, 0, 0, 1, 1, 1, 1, 0, 0, essentially all the uh, all possible ways of zeros and ones in three
So
places.
you are doing addition coordinate wise
Yes, sir.
and modulo 2.
Yes, sir.
So that will be Z2 cross Z2 cross Z2.
Yes, sir.
So that is abelian, but this is not abelian.
Oh, right. Okay, sir.
Okay. So that's why I told that there are more than two groups of order 8 which are abelian. So one is Z8, second is Z2 cross Z2 cross Z2, that three places group that you said. And there is one more group which is you can write either Z2 cross Z4 or Z4 cross Z2. So in one coordinate, you do calculations. So there are two coordinates. In one coordinate, you do calculations modulo 2, and in the other one, you do calculations modulo 4. So that group is not isomorphic to ZA, not to Z2. And you can see that by just looking at the order of elements. So there are three possibilities for abelian groups, and there will be just two for non-abelian groups. And it's a bonus fact. Groups of order p cube. So this is a group of order p cube, right? P raised to 3. Uh, P is equal to 2. All such groups have same uh, kind of same list of uh, groups. There are three abelian groups of the form ZP cube. Then second one is ZP square, direct product with ZP. Direct product means there are two coordinates. And third is ZP cross ZP cross ZP. And for non-abelian case, you need to generalize this Q8 and the other one is dihedral group, D8. So you can search in Google that if you are free, then what are the possibilities for groups of order PQ? As far as I know, then there should be just five possibilities. Three abelian and two non-abelian. And that I leave to you. And if I am wrong, then please correct me in the next class, okay?
Okay, sir. Thank you.
Okay. So now GH and second part is GH are both groups of order 37. So what you can say, G is isomorphic to H as both of them will be isomorphic to Z37. There is only one such group because 37 is a prime number. Okay. So
Okay, sir.
is there any doubt, or if not, then maybe we can stop here.
No doubt, sir. And sir, there was a slightly unrelated question, not related to topic, but the course itself.
Uh,
Um, so I got the exam notification,
right.
uh, and so this exam is online exam. So this means this doesn't have any pen and paper, right? It would only have MCQs, and everything would be um, inputted into the computer itself.
Right, but there can be like short answer type questions.
So in the short answer questions, if they ask the proof, so we'll have to type out the complete proof.
Uh, you just repeat, your voice just broke down.
So I just, if there are some proof type questions, does that mean that I have to type out the whole
No,
proof?
I don't think there will be proof questions.
Um,
There will
Can
be there will be just, I think, one word answer may be there. Some numeric number you might need to put. It will be very close. As far as I know, it will be very close to your practice assignment and assignments.
oh, okay, sir.
But there can be questions in which you need to put some value.
Oh, okay, sir.
Okay, so the
Uh,
proof-based questions, I don't think there will be there, but the proof can be asked in terms of the MCQ also.
oh,
So you may not need to prove, uh, but if you know the proof, it will be easier for you to uh, do the tick mark, right? So it can
yes, sir.
be right. The question can be reframed in terms of the MCQs because there can be questions in which more than one options are correct.
Yes, sir.
So then you might need to prove, but you need to just tick mark. But on your rough, you need to prove, and then only you will be able to do the tick mark. Okay.
Yes, sir. Sir, is can I access any of the previous year questions? Is there
Exam
any?
questions.
Yes, sir.
Exam questions. I don't know. Means you can mail to them if they are ready to share it with you. But I don't think it's available online.
Yeah, I searched online, it wasn't
It
available.
won't be available because they took the exam and so it's an online exam, so you don't get a copy of it, and they don't put it over their website as far as I know. So only the people who have given exams they know questions, and that's also whatever they could remember after the exam. So
Okay, sir.
okay. So shall I end the session now?
Yes, sir.
Okay. So thank you.
Thank you, sir.
We will meet on next Tuesday at the same time. Okay. And we will be discussing solution to assignment 4. Okay. Okay.
Okay, thank you.